I want to use this chart to summarize the things that you've learned and noticed about polynomials while doing the Desmos exploration. So first of all, let's just look at how a polynomial function is structured. There's a series of terms that add together, each of which have a coefficient, which may be 1, or it may be another number besides 1. It could be positive or negative, times x raised to a power. And that power needs to be an integer power, like 1, 2, 3, 4, etc. It cannot be a negative number. And then you have another coefficient times another x raised to a power that's 1 lower than that, and then another coefficient times x to a power 1 lower. Now, sometimes there'll be a term missing because that coefficient may be 0 for that particular term. Each one of these little clumps of a coefficient times x raised to a power is called a term. Terms in math are separated by addition, so this is considered a term. Notice that each term is actually a power function. A power function is just a constant times a number raised to a power. All of these numbers in front, of course, are called coefficients. The first coefficient, the coefficient on the highest degree term, the term with the highest exponent, is called the leading coefficient. The last term that does not have an x variable because it's like x to the 0 power is called the constant. The highest exponent is called the degree. Now let's look at some features of polynomial graphs. A polynomial graph can be either an odd degree function, in which meaning its highest exponent is an odd number, or it can be an even degree function, meaning its highest exponent is an even number. So odd degree functions always have endpoints that point the opposite directions. So if we have a positive leading coefficient, we would have something that look like this maybe, starting low and ending high. Notice overall from left to right it has a positive trend. A negative leading coefficient for an odd function, then I'm going to draw one that has a few more curves in it. So maybe this is like a 5th degree function. Okay, so it has several turns in it. But notice overall it goes downward from left to right. It has a negative trend. So as you go from left to right, are we in general going in the positive direction? As we go left to right, are we generally going to negative direction? Now it might change direction in between, but its endpoints are going generally from positive to negative. Now an even degree function has two endpoints that point the same direction. So you might have maybe a 4th degree function that looks kind of like this. Both endpoints are both up if we have a leading coefficient. If we have a even degree function with two endpoints pointing down, like this quadratic one here where they're both down, that means the leading coefficient is negative. Now you'll notice that they have different numbers of turning points. The maximum number of turning points that any function can have is 1 less than its degree. For example, in this degree 2 function, it can only turn 1 time. In a degree 4 function, notice it turns 1, 2, 3 times. So the maximum number of turning points it could have is 1 less than the degree. Now, the graphs also have a minimum number of turning points. For an odd degree function, the minimum number of turning points equals 0 because this one it doesn't have to change direction at all. So this one has no change in direction. Now, does that mean it has to have no change in direction? No. We could have something like this 5th degree polynomial which actually changes direction 4 times. But an odd degree function does not necessarily have to change direction. It might just have a little curve in it, but not actually go from up to down to back up again. Now an even degree function has to have at least one turning point. So an even degree, because an even degree function has its endpoints pointing the opposite direction, so it has to go from up to down or down to up at least one time to be an even degree function. So at least one change in direction. Now what about the y-intercept? Well, the y-intercept's kind of a gimme here. This is the same thing we do for any y-intercept. Let x equal 0. Y. Well, let me write that differently. It is the y value when x equals 0. Now, and of course you just let equal 0 and find y. Notice up here, if I have the polynomial written out in this form, which we call like the standard form of the polynomial, notice that if I put 0 in for x here, 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 the constant just ends up being the y-intercept. Now, x-intercepts. Let's talk about how many x-intercepts you can have. So if you think about the fact that, for example, a quadratic function could cross the x-axis twice, but it's not going to cross any more than twice. The maximum number of x, now it might not cross the x-axis at all. The maximum number of x-intercepts, it equals the degree of the function. So if it's a second degree function or a quadratic function, then it could have at most 2 x-intercepts. If it is a third degree, it could have 3, for example. X-intercepts are the real roots or zeros of the polynomial. When I say real, I mean not imaginary numbers. We can have imaginary numbers that are also zeros or roots of the polynomial, but they're not x-intercepts. More on that later. Now, this is an important theorem. The fundamental theorem of algebra says, well, we'll get to the actual theorem. Let's start with a little bit of background here. Values of x that make the function equal 0 are called zeros. That is what a zero is. It's a value of x that makes the function equal 0. In other words, let y equal 0 and find x. So these are x values that make the function equal 0. Every polynomial of degree n has exactly n complex zeros or roots. They're also called roots. So you might hear them called roots of the polynomial. That's another name for zeros of the polynomial. However, there are not necessarily n different or distinct zeros. When you see the word distinct in math, it means the same as different. There might not be n different zeros. Some zeros may be repeated. So we're going to look at an example in just a moment, and actually in the next little box here that shows an example of that. And you saw some examples where you had some repeated factors. It turns out repeated factors give you repeated zeros. So here I have a polynomial that is a 5th degree polynomial because it's x minus 2 times x minus 2 times x plus 1 times x plus 1 times x plus 1. If I multiply this all out, I have x squared times x to the third, which is x to the 5th. So this is a degree 5 polynomial, which means it should have exactly 5 zeros based on what we just said. Every polynomial. So this is the fundamental theorem of algebra that says every polynomial of degree n has exactly n complex zeros. Complex could be real or imaginary. So we have this factor x minus 2 squared, and we have another factor that's x minus 1 cubed. Well, we know that if I put 2 in for x, I would get 0, because I would have 0 squared times 3 squared, which would still be 0. If I put negative 1 in for x, I would also get 0, because I'd have 0 times negative 3 squared here. So both the number negative 1 and the number positive 2 give me a y-intercept or an x-intercept on this graph, or a place where y equals 0. Notice though what happens with the graph at those two numbers. At the place where I have x minus 2 squared, the graph just touches at positive 2 and turns around and comes back up. So the graph just touches the x-axis and looks similar to a parabola at the repeated 0. With an odd exponent on the factor, the x, that should say x plus 1. Oops, mistake here. X plus 1 cubed. The graph crosses the x-axis, but notice that as it crosses the x-axis, it makes a curve. And that curve, as it crosses the x-axis, looks very similar to a cubic graph, an x cubed graph. So notice when we look at other graphs, it just goes straight across the x-axis. If a graph goes straight across the x-axis, that means it's a factor that just is raised to the first power. But if it curves just as it goes across, so that point right here is a point of inflection on the graph, changing from concave down to concave up, then that indicates a 0 that's repeated an odd number of times, in this case 3 times. So notice at the bottom here I wrote there are still 5 zeros, but some are repeated. So we would consider the zeros to be 2, 2, -1, -1, -1, because there are actually 5 factors, x minus 2, x minus 2, x plus 1, x plus 1, x plus 1. So we say that those are repeated zeros. Sometimes I refer to this as a double zero and a triple zero. Sometimes you see the word a 0 of multiplicity 2 or a 0 of multiplicity 3. One more word about imaginary zeros, and I haven't shown you an example yet, but we're going to look at some examples of those in our next notes section. Imaginary zeros are not x-intercepts of the graph. So if you see a place where the graph crosses or touches the x-axis, that never indicates an imaginary zero. Imaginary zeros also occur in what are called conjugate pairs. And this is a direct result of finding them using the quadratic formula, and we'll see some examples of that in the next few days. For example, I might have an imaginary number that looks like this, 3 plus 2i, and another one that looks like 3 minus 2i. Conjugate pairs have the same first term and the last term, but the middle term is opposite signs. Another thing that we might have, another example of conjugate pairs would be negative 2i and positive 2i, because you could think of that as 0 minus 2i and 0 plus 2i. So those are also considered conjugate pairs. And those happen because of the plus or minus the radical in the quadratic formula.